Good morning, everyone. Many people have criticized Einstein's general theory of relativity and found fault that this is wrong or that is wrong, etc. And out of that, there was one person by the name of Herr Kretcshman. Attack on Einstein's general theory of relativity is considered to be a serious one and still being debated. And this YouTube about his attack and his criticism of Einstein's general relativity. So first let me read it and then I'm going to go through simplified version of his criticism. So Herr Kretcshman, 1917, this is what he says. The forms in which different authors have expressed the postulates of Lorenz Einstein theory. At that time it was called Lorenz Einstein theory, but today we just call Einstein's theory of general relativity. And especially the forms in which Einstein has recently expressed his postulate of general relativity admit the following interpretation. In the case of Einstein, it is required explicitly a system of physical laws satisfies a relativity postulate if the equations by means of which it is represented are covariant with respect to the group of spatio-temporal coordinate transformation associated with that postulate. If one accepts this interpretation and recalls that in the final analysis all physical observations consist in the determination of purely topological relations, coincidences between objects of spatio-temporal perception, from which it follows that no coordinate system is privileged by these observations, then one is forced to the following conclusion. By means of a purely mathematical reformulation of the equations representing the theory, and with at most mathematical complications, with that reformulation, any physical theory can be brought into agreement with any arbitrary relative postulate, even the most general one, and this without modifying any of its content that can be tested by observation. So I'm going to go through this in detail, but first I'm going to summarize what he's saying. Now, according to Albert Einstein's system, coordinate system has nothing to do with events. Okay, any coordinate system, I could pick any coordinate system and I should get the same predictions from somebody else's coordinate system. So the coordinate system has nothing to do with what's happening in the world, the events that they're called. So this is called the general covariance. And what Herr Kretcshman is saying, that if that is the case, that you could come up with a theory and then you would transform from one coordinate system to another coordinate system using some mathematical reformulation, and that way you would achieve general covariance, and then you say, okay, my theory is correct. But what he's saying, Herr Kretcshman, is that these mathematical constructs are not real. They are in our mind, they are human constructs. So that's what his argument. So Einstein's answer, I believe Herr Kretcshman's argument to be correct, but the innovation proposed by him not to be commendable. That is, if it is correct that one can bring any empirical law into generally covariant form, that means coordinate independent form, the principle, okay, generally covariant means coordinate independent. The principle A still possesses a significant heuristic or inherent force, which has already proved itself brilliantly in the problem of gravitation, and rests on the following of two theoretical systems. That is, two systems are Einstein's system and the Newton system. And that is all we have for gravity. That's all we have. Only two systems are working right now, and that is Newton's system and the Einstein system, and same thing at that time. The one is to be preferred, that is the simpler and more transparent, That's nonsense. Okay, I'm not going to read that. What Einstein saying, his equations are simpler, but then he added this: the principle of general relativity imposes exceedingly strong restrictions on the theoretical possibilities. Without this restrictive principle, it would be practically impossible for anybody to hit on the gravitational equation. So what he's saying, it is not easy as Herr Kretcshman says, just to come up with some equations. There are, it has to matches the observation, and Einstein is right. And this is 1917, the criticism, and now I'm doing this YouTube on almost 2022, and still we have only two theories on gravity. One is Newton's theory and the other one is Einstein's theory. So it's not easy to come up with another theory. But Herr Kretcshman says, if you come up with another theory and if you make it coordinate independent through covariance, and then that would achieve general covariance, that would be a mathematical construct. So I understand most people don't understand what we are saying, so we are going to go through the whole process. So let's see page 1. So I'm going to start with the page 1 here. So what is Albert Einstein's theory? It is a mathematical construct, or it is physical theory that exists in nature? That is the question. So what is relativity means anyway? If a system of coordinates k is chosen so that in relation to it physical laws hold good in their simple form, the same laws hold good in another coordinate system. Let's say coordinate system 2, page 2. So in my page 2, so what the relativity means, if you have a coordinate system x, y, and you said there are laws, and the laws x dash, y dash, and these laws, should be the same whether this coordinate system or that coordinate system. So the laws should not depend on the coordinate system. And normally we could see something called Lorenz transformation for non-accelerating systems, and you have x and t, x dash, t dash, and he's measuring t dash and he's measuring t, and there is a transformation properties like this: t dash equals 1 minus v squared with c squared, blah blah blah. And then we come to Minkowski invariance between two events. That would be page 1. Minkowski variation, something like this. This is page 3. So Lorentz transformation, and so Minkowski invariance. I'm just going through the special relativity stuff. I would assume everybody knows these things. So in Minkowski invariance, you have this invariance here. There are two events, event 1 and event 2. And this event we just call x1, y1, c1, t1. The other event is x2, y2, c2, t2. And this is the invariance: c squared t2 minus t1 squared, x2 minus, etc. And this can be represented in a matrix: c dt, dx, dy, dc in 1. So this is the Minkowski matrix, and then you would get this invariance. Okay, so this is for special theory of relativity. Okay, and now we go to page 5. Now Einstein notation, we could have this Minkowski matrix as ds squared eta mu nu dx mu dx nu, mu equals 0 to 1 to 3. I mean, I would assume you know these things, and this is special relativity. So we have this matrix here, and different numbers for each location. and when mu equals 0 and nu equals 0, mu 0, 0 is 1, and then your equation boils down to dx0 c squared dt squared, and etc. etc. Mu equals 1, nu equals 1, e1 1 becomes minus 1, eta, this is eta, right? Eta 1 1 is minus 1, eta 2 2 is minus 1, etc. So you would get, if you multiply this matrix with if you multiply here and then put mu equals 0 1 2 3, and then you would get the Lorenz transformation. So that's what it is, and so this is what you're going to get when you multiply. Now this value here is a constant. This is a constant in any coordinate system. C squared dt squared dx squared d minus dy squared minus dz squared is a constant. So if you have one event, and event 1 and event 2, and if you calculate this quantity, another person with another coordinate system, assuming they are not moving with acceleration, because we are talking special theory of relativity, assuming they are moving without acceleration, then this would be, both people would add these numbers together and come up with the same answer. So that's called an invariance. That's called invariance. But there is no such invariance in general relativity. This invariance is only for special relativity. In general relativity, you have covariance. So, and that was the basis for Kretcshman attack. Okay, so now let's go to general relativity, and here we have the equivalence principle, that is acceleration is equal to gravity. This principle allowed Einstein to state that there is no preferred acceleration. In special relativity, there is no special velocity or rest velocity or absolute space, and in general relativity, there is no preferred acceleration. And he used Newton's bucket experiment. I would assume you know that. Newton took a bucket and rotated it, and then he found it's concave, and he said this concave cannot be due to Earth, cannot be to the bucket. Then he says there is some absolute space out there, and that space, due to that space, this is rotating, and that's how its concavity is happening. And then this is just historical stuff I'm going through. And then you have the Mach's principle. The concavity was, Mach says no, it's not the absolute space. It's that due to when you're rotating, you are rotating the space across the space-time space here, and this space is not just in isolation. The distant stars have their gravity imposed upon the water, and that's why it's concaving, and Einstein agreed with that. And absolute space is not something that Einstein used. So let me see. And Einstein formulated Einstein tensor G based on masses around the space. Einstein tensor is related to T mu nu, that is the stress energy tensor, that depends on the mass. So Einstein's tensor G mu nu minus Riemann tensor and all that, the equation, so T mu nu is the mass energy. So let's see, I have written down better. So this is the curvature and this is the mass, and if you have mass, there is curvature. So the bucket is concaving due to the masses, and due to the masses you create a gravitational field, and that's why you see the concave nature of the bucket. So that's the Einstein argument. And when we go to something called Nth Wolf Theory, Nth Wolf means outline in his paper. This did not work. So what Einstein did was he took the Minkowski matrix and then added some values, dt squared. He added some coordinates, but that did not work. Nth Wolf was the first word in his paper. In German, he wrote that this did not work since the metric was flat. So this was understood by Einstein, that he cannot use a flat space-time and make it work. And then Einstein came up with something called hole argument. So he said, let's say there is a hole, there is no matter, and there is matter outside. So he has gravitational field and a metric tensor which represent the field. And let's say another person with another coordinate system has a different metric, and then if those two smoothly come towards the hole, these two matrices, he found that the answer would be different at one point and near the hole. So this was a problem, and Einstein found two metrics give two different values at the hole. So this became a big problem for him. And then there was this point coincidence argument. In this, events are coincidences at points. What this means is that, let's say there's an event and there's a particle moving like that, another particle moving like that, and they crash, and that's an event. Okay, this event has nothing to do with the coordinate system somebody picks. So let's say I have coordinate system A, another person has coordinate system B, and they calculate and they say, yeah, they're going to crash. And no matter what the coordinate system is, if they're going to crash, they're going to crash. That is real. Once these two particles crash, they would break into pieces. Now, that event is real, but the coordinate system that people use is not real. So that's what you could use any coordinate system and then calculate, and everybody should agree that they're going to crash or not crash, because that is a real event. The crashing or not crashing is a real event. That has nothing to do with the coordinate system. So this point is very important to understand Kretcshman argument. So measurement of the points are done using a coordinate system. For every event, there is a corresponding x1, x2, x3, and t coordinate. So every event happens in a space-time coordinates of x1, x2, x3, and time coordinate of t. So let's go to the next page. So event is a coincidence of particles or points, whatever. So coordinate system 1 and coordinate system 2 both should predict the 2 points would collide if they are going to collide. So now let's say person A has a coordinate system, let's call it 1. Person B has a coordinate system, let's call it 2. Transformation methodology to transfer between coordinate system 1 and 2. This is known as general covariance. So either one have a coordinate system and they both predict the same thing, and there has to be some kind of a transformation system going from one to the other. So this whole process is known as the general covariance, and this is different than the invariance that we talked about in Minkowski invariance, where there is a certain quantity is constant in all coordinate systems. We don't have that here. So the events are independent of coordinate system. So in this system, coordinate system is physically meaningless. That's what Hilbert said, one of the giants of the theory of relativity. So Einstein postulates basically principle of relativity, that is, the laws of nature are only assertions of time and space coincidences, and they have nothing to do with absolute space. Principle of equivalence, that would be acceleration and gravity are the same. And then the Mach's principle, which we discussed, gravitational field is determined by masses nearby and the universe as a whole. And then we have page 12. So page 12. So these are the postulates. So we go back to statement by. Now we go back to statement by Herr Kretcshman. So what now? I would assume you have the background now. What? So in special theory of relativity, we had an invariant quantity, c squared, d squared, dt squared minus x squared, y, blah, 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 and that was a constant throughout coordinate systems. In general theory of relativity, we don't have invariance. What we have is a covariance. That means every coordinate system would predict a certain event, not a certain law, a certain event. And no coordinate system is better than others, and each one should come up with the same event. If the 2 points are going to crash, each coordinate system should say that the 2 points are going to crash. So what is Herr Kretcshman saying? He's saying what Einstein did was he took those events, whatever happening on nature, and then he put a coordinate system onto it, and then he came up with a mathematical construct that would transform from one coordinate system to another, and then he showed that once you do the transformation, the coordinate system is not important and it's not part of nature. So you have events and some predictive ability that's not based on the coordinate system, but some relation between these events. I think you have to read this properly to understand what he's saying. So what he's saying is that whatever Einstein's theory of relativity is not a theory of nature. It's a mathematical construct that is producing. It is like, all right, let's see, let me try to see. Let's say we have a bunch of points. I'll put points here. Say we have a bunch of points, and say we have a bunch of points. Now, say like something like that. Okay, someone would come up with a curve that matches these points. That's what Einstein did. Basically, he came up with a equation. So let's see here. Okay, so we have a bunch of points, right? So we do a curve fitting equation for this. So we do a curve fitting equation for this. We fit a curve and we come up with an equation. And is that equation part of nature or it's just some mathematical construct? So we come up with some equation and we got a curve, something like that. Let's try another one. So we got a curve going through like that, and we say, okay, remove this one. So we have a curve like that, curve fitting equation. Now, is this curve fitting equation is part of nature or it's a mathematical construct? In this case, it's obviously a mathematical construct because we don't know what's going to happen. Let's say if we have another observation here, then this curve is not going to work. So what we did here is a curve fitting equation, not a law of nature. Okay, because if there's another observation out here, then this curve is not going to work. And that's exactly the point that Herr Kretcshman is saying. What Einstein did was he connected events and he came up with a theory and equations, his field equations, and then he showed that those field equations are independent of coordinates, so he called it general covariance. And Kretcshman is saying that's you are just fitting a curve to known events, known observations. It's not a law of nature. And this seems to be true. I mean, I could see his point. And many people even today accept that. Even Einstein did accept that. But Einstein said, wait, it's not just the mathematical construct. You just cannot come up with general covariance for any law, for instance, Newton's law. And people took the challenge. So people said, all right, let's see whether you could have Newton's theory of gravitation, put it into coordinate-free form. And they did. So that Einstein was wrong there. So you have coordinate-free form for Newton's laws, and unfortunately we have only two working theories. There are other gravitational theories out there, I forgot, there are a whole bunch of them, but they don't really work. Only two working theories, Albert Einstein theory and Newton's theory, both can be put into covariant form. So doesn't that make Herr Kretcshman right? Because he says if you come up with a theory, some kind of equation, and then you should be able to put it into covariant form. So he's saying this general covariance is something like a curve fitting theory. He did not use the word curve fitting. I'm just using it as an example. So if you have a bunch of points, you come up with some kind of a curve fitting equation. That's not a law of nature, because there could be a point that we don't have. And once you have that, if it is a law of nature, then this curve should go through this point too. This is the law of nature, but if it doesn't go through that, and so far, none of the observations. Now this criticism came in 1917, and now it's 2022 and 2021, and still there's nothing, no observation has found its way through to discredit Einstein's theory of general relativity. So, but there is a point there that Herr Kretcshman is making. It doesn't look like a theory of nature. It looks like some type of you're fitting the curve, some mathematical construct, and that's the heart of Kretcshman. That is basically what Kretcshman is saying. And